When a massive star dies, it's supposed to go out in one of the most violent events in the universe, a supernova. A blast so powerful it can briefly outshine an entire galaxy. That's what the textbooks say. That's what we expect. But here's something that most people have never heard about. Some stars don't do that. Some of the most massive stars in the universe reach the end of their lives, begin to collapse, and then just vanish. No blinding explosion. No expanding shell of gas racing across space. Nothing. The star is there one moment and gone the next, replaced by empty darkness and a black hole that swallowed everything, including the explosion itself. And the strangest part is, we may have already watched it happen. Before we get into this, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with what's supposed to happen. Before you can understand how a star fails to explode, you need to understand how a star successfully explodes. And the truth is, a normal supernova, the kind that works the way it's supposed to, is already one of the most extreme events in the known universe. It's so violent, so energetic, so fundamentally powerful that it challenges our ability to describe it even with the language of physics. A single supernova can briefly outshine an entire galaxy. Hundreds of billions of stars and one dying star match the light of all of them combined. That's not an exaggeration. That's not poetic license. That is a measured, observed, and confirmed fact. But to understand why some stars fail to produce this spectacle, we need to walk through the process step by step. We need to understand what's happening inside a massive star in the final moments of its life. And it begins, like most things in astrophysics, with gravity. Every star is a balancing act. Gravity pulls inward, trying to crush the star into its center. Nuclear fusion pushes outward, generating energy by fusing lighter elements into heavier ones. As long as these two forces remain in equilibrium, the star is stable. It shines. It can do this for millions or billions of years, depending on its mass. Our Sun is a relatively small star with billions of years of fuel remaining. But the stars we're interested in tonight are different. Massive stars. Stars at least 8 times the mass of the Sun, and often much more. These stars live fast and die young. A star with 25 times the mass of the Sun might burn through its entire fuel supply in only about 7 million years, less than 1% of the Sun's lifetime. These massive stars are the ones that produce supernovae. And the reason has everything to do with what happens inside them as they run out of fuel. When a massive star exhausts the hydrogen in its core, fusion doesn't simply stop. The core contracts, heats up, and when the temperature reaches about 100 million degrees Celsius, helium nuclei start fusing together into carbon and oxygen. The star has found a new fuel source and stabilizes again, at least temporarily. But helium fusion doesn't last as long as hydrogen fusion did. In a star of 25 solar masses, the core might burn through its helium in roughly 700,000 years. That's a fraction of the time hydrogen lasted. When the helium runs out, the core contracts again, heats up again, and begins fusing carbon into neon, magnesium, and sodium. Carbon burning lasts even less time, maybe 600 years in a star of this mass. Then the carbon runs out, the core contracts, heats up further, and neon fusion begins. Neon burning might last about a year. After neon, oxygen fuses into silicon and sulfur. Oxygen burning lasts perhaps 6 months. Each successive fuel burns faster than the last. The star is racing through its reserves at an accelerating pace, and it has no way to slow down. Gravity demands fuel, and the star keeps finding it, but each new fuel source produces less energy than the one before and is exhausted more quickly. And then comes the final stage, silicon fusion. This is where things take a truly dramatic turn. When the temperature at the core reaches about 3 billion degrees Celsius, silicon nuclei begin fusing together. And the product of silicon fusion is iron. Specifically, isotopes of iron and nickel at the very peak of the nuclear binding energy curve. Silicon burning is ferocious. It lasts about 1 day. In some models, it can be as short as a few hours. Think about that progression. Hydrogen burning lasted millions of years. Helium lasted hundreds of thousands of years. Carbon lasted centuries. Neon lasted about a year. Oxygen lasted months. Silicon lasts a single day. The star is burning through fuel at an almost incomprehensible rate, and now it has reached the end of the line. Iron is the end of the road for nuclear fusion, and this is absolutely critical to understanding everything that follows. Every fusion reaction up to this point has been exothermic, meaning it releases energy. When hydrogen fuses into helium, energy comes out. When helium fuses into carbon, energy comes out. All the way through silicon fusing into iron, each step releases energy that helps support the star against gravitational collapse. But iron is different. Iron sits at the very peak of the nuclear binding energy curve. This means that fusing iron into heavier elements does not release energy. It consumes energy. It's endothermic. The star cannot extract energy from iron. It's like trying to burn ash. There's nothing left to get out of it. And this is the moment the star is doomed. Because the star has been fighting gravity its entire life using the energy from fusion. Hydrogen fought gravity. Helium fought gravity. Carbon, neon, oxygen, silicon. Each one took its turn holding the star up against the relentless inward pull. But now, with an iron core sitting at the center of the star, there is no more fuel. There's nothing left to burn. There's no new fusion reaction that can save the star. Gravity has been patient. It has been pulling inward for millions of years, and fusion has been pushing back. But now, for the first time in the star's life, gravity wins. What happens next unfolds with terrifying speed. The iron core has been growing as silicon fusion adds more iron to it. And the core is held up not by fusion, because there is no fusion happening in the iron, but by a quantum mechanical effect called electron degeneracy pressure. This is the pressure created by electrons resisting being squeezed too close together, a consequence of the Pauli exclusion principle in quantum mechanics. Electrons don't like to share the same quantum state, and this resistance creates a pressure that can support the core, but only up to a point. That point is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in the early 1930s. The limit is about 1.4 times the mass of the Sun. As long as the iron core remains below this mass, electron degeneracy pressure can hold it up, but the core keeps growing as silicon burning adds more iron. And the instant the core exceeds the Chandrasekhar limit, electron degeneracy pressure fails, not gradually, not slowly. It fails catastrophically, all at once. The core collapses. And when I say collapses, I mean it collapses fast. The inner core, roughly the mass of the Sun compressed into a volume about the size of Earth, falls inward at speeds reaching 70,000 kilometers per second. That's roughly 23% of the speed of light. The entire inner core collapses in less than a second. In about a quarter of a second, a region the size of Earth is compressed down to a ball roughly 20 kilometers across. It goes from thousands of kilometers wide to a city-sized object in a fraction of a heartbeat. During this collapse, the density becomes so extreme that protons and electrons are squeezed together, merging to form neutrons. This process is called neutronization, and it releases a flood of ghostly particles called neutrinos. These neutrinos carry away an enormous amount of energy. In fact, the total energy released in neutrinos during a core collapse is staggering, roughly 3 × 10 to the 46 joules. To put this in perspective, this is roughly 250 times more energy than the Sun will produce over its entire 10 billion year lifetime, and nearly all of it comes out in neutrinos in about 10 seconds. The collapsing core doesn't just keep falling forever. When the density reaches about 2 to 3 times the density of an atomic nucleus, the strong nuclear force between neutrons suddenly resists further compression. The core becomes essentially incompressible. Think of it like a ball being dropped onto a hard surface. The inner core hits this wall of nuclear density and bounces. The infalling material rebounds outward, sending a shock wave racing back up through the still collapsing outer layers of the core. This is the birth of the supernova shock. This is the moment where, if everything goes right, the star explodes. But here's the problem. And this is something that took physicists decades to fully appreciate. The shock wave, powerful as it is, doesn't have enough energy on its own to blow the star apart. As the shock moves outward through the outer core, it runs into the iron that's still falling inward. This infalling material is dense and heavy. The shock has to push against it, and in doing so, it loses energy. The shock also loses energy through a process called photodisintegration. As the shock passes through the iron, the extreme temperatures break the iron nuclei apart into individual protons and neutrons. This takes energy. It costs the shock wave dearly. Every iron nucleus that gets torn apart absorbs energy that the shock needed to keep going. Within milliseconds, the shock stalls. It stops moving outward. It just sits there, a standing accretion shock, hovering at a radius of roughly 100 to 200 kilometers from the center. At this point, the star is in a critical state. The shock has stalled. Material is still raining down onto it from above. If nothing revives the shock, the star will not explode. Everything will fall inward and form a black hole. This is the knife edge on which a supernova balances. So what revives the shock? Neutrinos. Remember the enormous flood of neutrinos released during the collapse of the core? Most of these neutrinos escape the star entirely. Neutrinos are famous for barely interacting with matter. They pass through the Earth without noticing it's there. But the conditions behind the stalled shock are so extreme, the densities are so high, that a small fraction of the neutrinos are absorbed by the material just behind the shock. This absorption deposits energy into the region between the newborn neutron star and the stalled shock, a zone that scientists call the gain region. It's called that because it's where material gains energy from neutrino absorption. This energy heats the material, creates turbulence and convection, and gradually pushes the shock outward. This process is called the neutrino-driven mechanism, and it is the leading explanation for how core collapse supernovae work. The neutrinos effectively transfer energy from the collapsing core to the stalled shock, reviving it and giving it enough energy to tear the star apart. When the shock is successfully revived, it accelerates outward through the star. It takes several hours for the shock to travel from the core to the surface, depending on the size of the star. But when it reaches the surface, the result is spectacular. The outer layers of the star are ejected into space at speeds of thousands to tens of thousands of kilometers per second. The material is heated to billions of degrees. New elements are forged in the explosion itself. Elements heavier than iron, including gold, platinum, and uranium. These elements are created by the intense neutron bombardment that occurs during the explosion, a process called rapid neutron capture. The ejected material forms an expanding cloud of gas and dust, called a supernova remnant. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. Nearly 1,000 years later, the remnant is still expanding, still glowing, a tombstone and a birthplace all at once, because the elements scattered by that explosion eventually became part of new gas clouds, new stars, new planets, the iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of it was forged inside a massive star and scattered across space by a supernova explosion. You are literally built from the debris of dead stars. At the center of the supernova remnant, the collapsed core remains. If the core is below about 2 to 2.5 solar masses, it stabilizes as a neutron star, an object roughly 20 kilometers across, but containing more mass than the Sun. The density is almost beyond comprehension. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. Some neutron stars spin rapidly, emitting beams of radiation that sweep through space like cosmic lighthouses. We call these pulsars. The Crab Nebula contains a pulsar at its center, spinning about 30 times per second, the beating heart of a dead star. If the remaining core is more massive than about 2 to 2.5 solar masses, even neutron degeneracy pressure cannot support it, and it collapses further into a black hole. In a successful supernova, this black hole forms from whatever material falls back onto the neutron star after the explosion, not from the entire star. The explosion has already thrown most of the star's mass into space. Only a fraction remains to form the compact remnant. The most famous recent supernova, and the one that confirmed many of these ideas, was SN 1987A. On February 23rd, 1987, a supernova was detected in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 168,000 light-years away. It was the closest supernova observed since the invention of the telescope, and crucially, about 3 hours before the visible light from the explosion reached Earth, neutrino detectors on Earth picked up a burst of neutrinos. The Kami-Okande detector in Japan detected 11 neutrinos. The IMB detector in the United States detected 8. A few other detectors picked up additional events. In total, about 25 neutrinos were detected from SN 1987A across multiple facilities. 25 neutrinos. That might sound like nothing. But consider this. The supernova released roughly 10 to the 58 neutrinos in total. The overwhelming majority of those neutrinos pass through the Earth without interacting with anything at all. The fact that we caught even 25 of them from a supernova in another galaxy is remarkable. And those 25 neutrinos confirmed what theorists had predicted. The core collapse produces an enormous burst of neutrinos before the visible explosion appears. The neutrinos arrived first because they escape the collapsing core almost immediately, traveling at nearly the speed of light. The visible light takes hours to emerge because the shock wave has to travel from the core to the stellar surface before the star brightens. Those 25 neutrinos were one of the most important observations in the history of astrophysics. They confirmed that core collapse produces a neutron star. They confirmed the energy scale of the collapse. They confirmed that neutrinos carry away the vast majority of the gravitational binding energy. They confirmed our basic picture of how massive stars die. The progenitor star of SN 1987A was identified in earlier photographs. It was a blue supergiant called Sandu Leak-69202, with a mass of roughly 18 to 20 times the mass of the Sun. After the explosion, astronomers searched for a neutron star at the center of the expanding debris. For decades, they couldn't find one definitively, which led to speculation that a black hole might have formed instead. But in 2024, observations from the James Webb Space Telescope provided strong evidence for a neutron star at the center of the remnant, emitting infrared radiation consistent with a young, cooling neutron star. The system appeared to have produced a successful supernova and left behind a neutron star, just as the standard theory predicts. So, this is what a normal core collapse supernova looks like. A massive star burns through its fuel in a specific sequence: hydrogen, helium, carbon, neon, oxygen, silicon. Each fuel runs out faster than the last. An iron core builds up at the center. When that core exceeds the Chandrasekhar limit, it collapses in less than a second. A shockwave forms, but stalls. Neutrinos revive the shock. The shock tears the star apart. The outer layers are ejected into space at thousands of kilometers per second. Heavy elements are forged and scattered. A neutron star or a small black hole is left behind. The explosion shines brighter than billions of stars for weeks or months before fading. This is the expected ending for a massive star. This is what the physics predicts when everything works the way it's supposed to. This is the textbook death of a star. Violent, dramatic, luminous, unmissable. But here is the question that physicists began seriously asking in the late 20th century and into the 21st. What happens when the shock doesn't get revived? What happens when those neutrinos aren't enough? What happens when the infalling material is too heavy, too dense, too tightly bound for the shock to push through? What happens when gravity doesn't just win the battle at the core, but wins the entire war? Because the neutrino-driven mechanism is not guaranteed to work. It doesn't work every time in computer simulations. It depends on the mass of the star, the structure of the core, the density of the layers above the core, the metallicity of the star, and a dozen other variables that change from star to star. In some simulations, the shock is revived and the star explodes beautifully, but in others, the shock stalls, weakens, and never recovers. The material keeps falling inward. The proto-neutron star at the center accumulates more and more mass, and when it crosses the threshold, when it exceeds the maximum mass that even neutron degeneracy pressure and the strong nuclear force can support, it collapses into a black hole. And when that happens, the black hole doesn't just sit there politely. Its event horizon expands outward, swallowing the proto-neutron star, swallowing the stalled shock, swallowing the infalling material. Everything that was trying to become a supernova, everything that was on the verge of exploding, gets consumed. The explosion that should have happened, the explosion that would have scattered elements across space and lit up the sky, that explosion is eaten. The star doesn't explode. It doesn't scatter its elements across space. It doesn't leave behind a glowing remnant or a pulsar spinning in the debris. It just disappears. One moment, there is a massive star shining in the sky. The next moment, there is a black hole and silence. That is a failed supernova, and understanding how and why it happens is what we're going to explore next. So now you understand how the process is supposed to work. The iron core collapses. A shockwave is born. Neutrinos revive that shock. The star explodes. A neutron star or a small black hole is left behind. That's the textbook version. That's the clean story. But nature doesn't always follow the textbook. And what physicists have come to realize over the past few decades is that this process, this delicate mechanism where neutrinos rescue a dying shockwave, is not robust. It's not guaranteed. It doesn't always succeed. In fact, there are very good reasons to believe that for some massive stars, the shockwave that forms during core collapse never gets revived at all. The neutrinos pour out of the collapsing core just like they're supposed to. The shock forms and stalls just like it's supposed to. But then, instead of being pushed back to life, the shock just sits there, weakening, while more and more material crashes down onto it from above. The shock doesn't recover. The material keeps falling. And eventually everything, the stalled shock, the proto-neutron star, the infalling gas, all of it crosses the event horizon of a newly forming black hole. The star doesn't explode, it collapses, directly, completely, and almost silently. This is what astrophysicists call a failed supernova, and sometimes more precisely, a direct collapse to a black hole. To understand why this happens, we need to go deeper into the physics of the shock revival mechanism. Because the failure of a supernova isn't random. It isn't bad luck. It's physics. Specific conditions inside certain stars make the explosion mechanically impossible, or at least extraordinarily unlikely. And those conditions come down to a battle, a tug of war between two competing forces at the most extreme moment of the star's life. On one side, you have the energy being deposited behind the stalled shock by neutrinos. This is the engine trying to drive the explosion. Neutrinos stream outward from the surface of the proto-neutron star, and a small fraction of them are absorbed by the dense material sitting just behind the shock in the gain region. This absorption heats the material, increases the pressure, and pushes the shock outward. The more neutrino energy that gets absorbed, the stronger the push. On the other side, you have the ram pressure of the material falling inward. Above the shock, the outer layers of the star are still collapsing. They're falling toward the center at enormous speeds, crashing into the shock from the outside. This infalling material pushes the shock inward, trying to crush it. The more material that's falling in, and the faster it's falling, the harder it is for the neutrino-heated material to push the shock outward. So, the question of whether a star explodes or not comes down to this. Can the neutrino energy deposited in the gain region generate enough pressure to overcome the ram pressure of the infalling material? If yes, the shock revives and the star explodes. If no, the shock remains stalled, the material continues to accumulate, and the proto-neutron star grows until it can no longer support itself. At that point, it collapses into a black hole, and the event horizon expands outward, swallowing everything. This is why the mass of the progenitor star matters so much. More massive stars have more material pressing down on the shock. The ram pressure is higher. The shock has to push against a heavier load, And if the load is heavy enough, the neutrino energy simply isn't sufficient to overcome it. But it's not just total mass that matters. What matters even more is something called the binding energy of the stellar envelope. The binding energy is essentially a measure of how tightly the outer layers of the star are gravitationally bound to the core. A star can have a lot of mass, but if that mass is spread out over a very large volume, it might not be as tightly bound. Conversely, a star with a more compact structure might have a higher binding energy even at a lower total mass. The binding energy determines how much work the shock has to do to eject the outer layers. If the binding energy is high, the shock needs more energy to unbind the material and throw it into space. If the neutrino mechanism can't deliver that much energy, the explosion fails. This is where the internal structure of the star becomes crucial. Not all massive stars look the same on the inside when they reach the end of their lives. Two stars with the same total mass can have very different core structures, very different density profiles, and very different binding energies. And these differences can determine whether one star explodes and the other doesn't. One of the key factors that shapes a star's internal structure is something called compactness. Compactness, in this context, is a parameter that describes how concentrated the star's mass is toward the center. A star with high compactness has a lot of mass packed into a relatively small radius. A star with low compactness has its mass spread out more evenly. Researchers like Christian Ott, Evan O'Connor, and others developed a compactness parameter that can be calculated from the structure of a star just before core collapse. What they found is striking. Stars with high compactness are much more likely to fail to explode. Stars with low compactness are more likely to produce successful supernovae. The reason is intuitive once you understand the physics. High compactness means more mass at smaller radii. When the core collapses, that mass falls inward quickly, creating intense ram pressure on the shock. The shock has to fight against a dense, fast-moving wall of material, and in many cases, it loses that fight. Low compactness means the mass is more spread out. The material falling onto the shock arrives more gradually, giving the neutrino mechanism more time to work. The shock has a better chance of being revived before it's overwhelmed. Here's what makes this even more interesting. Compactness doesn't increase smoothly with stellar mass. You might expect that more massive stars always have higher compactness, making them more likely to fail. But that's not what the models show. The relationship between mass and compactness is complicated, even chaotic. A star of 22 solar masses might have low compactness and explode successfully. A star of 23 solar masses might have high compactness and fail. A star of 25 solar masses might have low compactness again and succeed. The pattern is jagged and non-monotonic. This happens because of the complex history of nuclear burning in the star's core. Each stage of burning, hydrogen, helium, carbon, neon, oxygen, silicon, leaves behind shells and layers with different compositions and densities. The exact details depend sensitively on the mass, on the rate of burning, on how convection mixes material between layers, and on a host of other factors. Small differences in the initial mass of the star can lead to very different internal structures by the time the iron core forms. This sensitivity is sometimes compared to the butterfly effect in chaos theory. A tiny change in initial conditions leads to a dramatically different outcome. Researchers like Suk-Bold, Woosley, and Heger published landmark studies mapping out which initial stellar masses lead to explosions and which lead to failed supernovae. Their work, based on detailed one-dimensional stellar evolution models, showed that the outcome is not a simple function of mass. There are islands of explodability and islands of failure scattered across the mass range. Some mass ranges consistently produce explosions, others consistently fail, and some are right on the boundary where the outcome might depend on details too subtle to capture in current models. That said, there is a general trend that emerges from these studies. Stars at the lower end of the massive star range, those between about 8 and roughly 15 to 20 solar masses, tend to explode more reliably. Their envelopes are less tightly bound. Their compactness tends to be lower. The neutrino mechanism has an easier time reviving the shock. These stars produce the supernovae we observe most frequently. At higher masses, particularly above about 20 to 25 solar masses, the situation becomes more uncertain. Some of these stars explode, others don't. The outcome depends on the detailed structure of the star, which in turn depends on its entire evolutionary history. And at the very highest masses, above roughly 40 solar masses, the likelihood of failure increases significantly in many models. These are the stars with the most material pressing down on the shock, the highest binding energies, and the most challenging conditions for the neutrino mechanism to overcome. But mass alone doesn't tell the whole story. Another critical factor is metallicity. In astronomy, metallicity refers to the fraction of a star's composition that consists of elements heavier than hydrogen and helium. Astronomers, somewhat confusingly, call all elements heavier than helium metals, even things like carbon and oxygen that no chemist would consider metallic. Metallicity matters because it affects how a star loses mass during its life. Massive stars don't just sit quietly and burn fuel. They blow material off their surfaces in powerful stellar winds. These winds are driven by the pressure of the star's own radiation pushing on atoms in the outer atmosphere. And here's the key point. Heavier elements are better at absorbing and scattering radiation. A star with higher metallicity has more of these heavy elements in its atmosphere, which means its winds are stronger. Stronger winds mean the star loses more mass over its lifetime. A star that starts out at 40 solar masses might lose 10 or 15 solar masses through winds over the course of its life, arriving at the moment of core collapse with only 25 or 30 solar masses remaining. This mass loss can make the difference between explosion and failure. By shedding mass, the star reduces the weight of the material pressing down on the shock. It reduces the binding energy of the envelope. It makes the explosion easier. So a high metallicity star at 40 solar masses might successfully explode because it has lost enough mass through winds. But a low metallicity star at the same initial mass, one that formed from pristine gas with very few heavy elements, retains most of its mass. Its winds are weak. It arrives at core collapse with nearly all of its original 40 solar masses intact. The envelope is massive and tightly bound. The shock has far more material to fight through, and the explosion is far more likely to fail. This has an important implication. In the early universe, when metallicity was low because not many generations of stars had yet lived and died to enrich the gas with heavy elements, failed supernovae may have been more common. The first generations of massive stars, born from nearly pure hydrogen and helium, would have retained most of their mass. They would have had massive, tightly bound envelopes, and many of them may have collapsed directly into black holes without producing visible explosions. This could help explain the origin of some of the more massive stellar mass black holes we've detected through gravitational wave observations. Black holes of 30 or 40 solar masses are difficult to explain if every massive star loses significant mass through winds and then explodes, ejecting even more mass. But if some stars skip the explosion entirely and collapse whole, retaining most of their mass, then producing a 30 or 40 solar mass black hole becomes straightforward. Now, let me be precise about what physically happens during a failed supernova, because the details matter and they're different from what happens in a successful explosion. In a failed supernova, the iron core still collapses. The Chandrasekhar limit is still exceeded. The core still falls inward at a significant fraction of the speed of light. A proto-neutron star still forms. The bounce still happens. A shock wave is still born. Neutrinos are still released in enormous quantities. Up to this point, the failed supernova looks exactly like a successful one. The difference comes in what happens next. In a successful supernova, the neutrino energy revives the shock within a few hundred milliseconds. The shock begins to move outward, slowly at first, then faster. Within a second or so, the explosion is underway. Material is being ejected. The star is dying in a blaze of light. In a failed supernova, the shock stalls and stays stalled. The neutrino energy isn't enough. The ram pressure of infalling material is too strong. The shock hovers at roughly 100 to 200 kilometers from the center, unable to advance. Meanwhile, material continues to pile up on the proto-neutron star. The proto-neutron star grows more massive. It heats up. It radiates neutrinos even more intensely as it's compressed. But the neutrinos are escaping, carrying away energy that the proto-neutron star needs to support itself. There is a maximum mass that a neutron star can sustain. This is called the Tolman-Oppenheimer-Volkoff limit, and it's somewhere between about 2 and 2.5 solar masses, though the exact value depends on the equation of state of ultra-dense matter, which is still not perfectly known. When the proto-neutron star exceeds this limit, neutron degeneracy pressure and the repulsive component of the strong nuclear force can no longer support it. The object collapses into a black hole. The formation of the black hole is rapid. The event horizon appears at the center and expands outward. Within milliseconds, it engulfs the entire proto-neutron star. The neutrino emission, which had been pouring out of the proto-neutron star's surface, abruptly shuts off. This is a crucial signature. In a successful supernova, neutrino emission from the proto-neutron star continues for seconds, gradually declining as the neutron star cools. In a failed supernova, the neutrino signal is suddenly cut short when the black hole forms. The neutrinos simply stop. If we ever detect a neutrino burst from a collapsing star that cuts off abruptly rather than fading gradually, it would be powerful evidence that a black hole formed and the explosion failed. Once the black hole forms, the stalled shock collapses inward along with everything else. The infalling material streams past the event horizon. The outer layers of the star, which were still falling inward, continue falling. In many models, most of the star's mass ends up inside the black hole. There is no explosion to eject it. There is no shock wave to scatter it across space. The material simply falls in. But there's an important nuance here. In some scenarios, not absolutely everything falls into the black hole. The outermost layers of the star, particularly if the star is a red supergiant with an enormous, loosely bound hydrogen envelope, might not be gravitationally bound tightly enough to fall in completely. When the core collapses and the neutrino burst carries away a significant amount of energy and mass equivalent, the gravitational pull on the outermost layers briefly decreases. This can unbind a small fraction of the envelope. In some models, this produces a weak, low-energy transient, a brief brightening far fainter than a normal supernova. In others, the outer envelope simply drifts away slowly as the gravitational anchor at the center disappears into the black hole. But the key point is that even in scenarios where some material escapes, the event looks nothing like a real supernova. There is no powerful shock tearing through the star. There is no brilliant flash of light rivaling a galaxy. There might be a faint glow, a brief dimming and reddening, or simply a star that fades from view over months or years. The contrast with a successful supernova could not be more stark. It's also important to distinguish a failed supernova from other types of stellar death that produce faint or unusual transients. Not every dim explosion is a failed supernova. Some stars produce weak supernova because they're at the low end of the mass range, barely above the threshold for core collapse. These stars might produce genuine but faint explosions. Others produce unusual transients because of binary interactions, where a companion star strips material from the dying star before it collapses. These are different phenomena with different physical mechanisms. A failed supernova specifically refers to a star whose core collapses, forms a shock, fails to revive that shock, and collapses into a black hole without producing a normal explosion. The distinction is in the mechanism, not just the brightness. Another point worth clarifying is the difference between a failed supernova and a direct collapse that happens through a different pathway. In the very early universe, first-generation stars formed from primordial gas with near-zero metallicity could grow to enormous masses. The most extreme of these, above about 260 solar masses, could collapse directly into black holes without forming a proto-neutron star at all, driven by electron-positron pair production instabilities. This is sometimes also called direct collapse, but it's a fundamentally different process. In our case, the star goes through the normal core collapse process, forms a proto-neutron star, launches a shock, and then fails. The pair instability pathway is a different mechanism entirely, relevant only to the most massive stars in the very early universe. The physics of shock revival is extraordinarily difficult to simulate. For decades, most simulations of core collapse supernovae were done in one dimension, meaning they assumed the star was perfectly spherically symmetric. In these one-dimensional simulations, almost no stars exploded. The neutrino mechanism failed nearly every time. This led to a major crisis in the field. The theory predicted that core collapse should produce supernovae. We observe supernovae all the time, and yet the simulations couldn't produce them. The resolution came when researchers moved to two-dimensional and eventually three-dimensional simulations. In multiple dimensions, convection and turbulence develop behind the stalled shock. Hot, buoyant plumes rise upward while cooler material sinks downward. This convective overturn increases the efficiency of neutrino heating by cycling fresh material through the gain region. A parcel of gas absorbs neutrino energy, rises, gets replaced by cooler gas that descends, and absorbs more energy. This turbulent mixing extends the time material spends in the gain region and increases the total energy absorbed. Additionally, a large-scale instability called the standing accretion shock instability, or SASI, can develop. This causes the shock to oscillate and deform, sloshing back and forth in large-scale motions. These motions further increase the effective area of the shock, push it to larger radii, and help the neutrino mechanism succeed. When these multi-dimensional effects are included, many more simulations produce successful explosions, but not all. Even in the most sophisticated three-dimensional simulations running on the most powerful supercomputers in the world, some stars still fail to explode. The most massive progenitors, the ones with the highest compactness and the most tightly bound envelopes, resist explosion even when convection and SASI are operating at full strength. The neutrino energy, amplified by all these multi-dimensional effects, is still not enough to overcome the ram pressure. The shock still stalls permanently. The proto-neutron star still grows beyond its limit, and a black hole still forms. This is not a failure of the simulations. This is the physics telling us something real. Some stars are simply too massive, too compact, too tightly bound to explode. The mechanism that works for a 15 solar mass star doesn't work for a 40 solar mass star. The same physics, the same neutrino mechanism produce different outcomes depending on the properties of the progenitor. And this has profound implications for how we understand stellar death. For a long time, the standard picture was simple. Massive stars explode as supernovae. Low-mass stars shed their outer layers gently and become white dwarfs. Everything above the 8 solar mass threshold produces a supernova. But the reality now emerging from decades of theoretical work and increasingly sophisticated simulations is more complex and more interesting. There appears to be a landscape of outcomes. Some massive stars explode brightly, producing the classic supernova we observe. Others explode weakly, producing faint transients that might be overlooked in surveys. And some don't explode at all. They collapse directly into black holes, swallowing their own deaths, leaving behind nothing but darkness and a gravitational signature. The fraction of massive stars that fail to explode is still debated. Different research groups, using different stellar evolution models and different simulation methods, get different answers. Some estimates suggest that roughly 20 to 30% of all massive stars above 8 solar masses fail to produce a visible supernova. Others suggest the fraction might be lower, perhaps 10 to 15%. The exact number depends on assumptions about stellar winds, metallicity, convective mixing, binary interactions, and the nuclear physics of the equation of state. But virtually all modern studies agree on the central point. Not every massive star explodes. Some of them die quietly. And this quiet death, this failure to produce the expected fireworks, is not a rare curiosity or a theoretical edge case. It may be a significant channel of stellar death, responsible for producing a substantial fraction of the stellar mass black holes in the universe. What's truly remarkable about this is the contrast. A successful supernova is one of the most luminous events in the cosmos. It outshines billions of stars. It scatters newly forged elements across light years of space. It leaves behind a glowing remnant that persists for thousands of years. It's visible across galaxies, sometimes across the observable universe. A failed supernova is the exact opposite. The same initial process, the same core collapse, the same iron core exceeding the Chandrasekhar limit, the same shock formation, but with a completely different ending. Instead of an explosion that outshines a galaxy, there is silence. Instead of light, there is darkness. Instead of creation, scattering new elements to seed future generations of stars and planets, there is consumption. The the black hole eats everything. The elements that star spent millions of years forging in its core, the carbon, the oxygen, the silicon, the iron, all of it vanishes behind the event horizon, locked away from the universe forever. The universe's most massive collapses don't always produce its most brilliant explosions. Sometimes the biggest stars die with the least fanfare, and the only way we can hope to catch them in the act is by watching carefully for stars that simply disappear, which is exactly what astronomers have been trying to do. And that story, the story of what a failed supernova actually looks like from the outside, and the extraordinary challenge of finding one, is where we go next. So now we understand the physics. We understand how the shock can fail, how the proto-neutron star can grow beyond its limit, how the black hole can form and swallow everything. But there's a question that matters just as much as the theory. If a star dies this way, if it collapses into a black hole without a proper explosion, what does it actually look like? What would you see if you were watching that star through a telescope? Because here's the challenge. Astronomers can't look inside a star. We can't watch the shock wave stall. We can't see the proto-neutron star growing more massive. We can't observe the event horizon forming and expanding. All of that happens deep inside the star, hidden beneath thousands of kilometers of stellar material. What we can observe is the surface of the star and what happens to the light it emits. And the truth is, a failed supernova would be one of the most subtle and difficult events to detect in all of observational astronomy. Because the defining feature of a failed supernova isn't a flash. It's an absence. It's a star that was there and then wasn't. Let's walk through what the models predict an observer would see, step by step. Before the collapse, the star looked normal. If it's a red supergiant, which many of the best candidates for failed supernovae are, it appears as a cool, luminous star with a surface temperature of about 3,000 to 4,000 degrees Celsius. Red supergiants are enormous. Their radii can be hundreds of times the radius of the Sun. Betelgeuse in the constellation Orion is a famous example, though there's no specific reason to think Betelgeuse will produce a failed supernova. The point is that these are big, bright, easily visible stars. They're among the most luminous stars in any galaxy. You can spot them in nearby galaxies with a decent telescope. They show up clearly in images. They're catalogued and monitored. Then the core collapses. Everything we discussed earlier happens inside the star in a matter of seconds. The iron core exceeds the Chandrasekhar limit. The core falls inward. A proto-neutron star forms. A shock wave is born and stalls. Neutrinos pour out. And then the shock fails to revive. The proto-neutron star grows past the Tolman-Oppenheimer-Volkoff limit. A black hole forms. All of this happens in seconds to minutes. But from the outside, nothing visible has happened yet. The surface of the star is hundreds of times the radius of the Sun, and information about the core collapse travels outward at a finite speed. The surface doesn't know the core has collapsed yet. Light still pours from the photosphere as if nothing has changed. The star looks exactly the same as it did moments before. But then, something does change. When the black hole forms, the gravitational field at the center of the star shifts. The proto-neutron star that was sitting at the center, radiating neutrinos, suddenly disappears behind the event horizon. The neutrino luminosity drops to 0 almost instantaneously. This neutrino emission had been carrying away energy and mass equivalent from the core. When it stops, the effective gravitational mass at the center changes slightly. More importantly, The pressure support provided by the neutrino heated material behind the shock vanishes. The shock, already stalled, collapses inward. Material that had been hovering behind the shock falls into the black hole. Now, here's where the observable signature depends on the type of star. If the star has a massive, loosely bound hydrogen envelope, as red supergiants do, something interesting can happen. The sudden loss of pressure support and the change in gravitational binding can send a weak disturbance outward through the envelope. As the core disappears and the inner layers of the star fall into the black hole, the outermost layers of the hydrogen envelope may not be tightly enough bound to follow. Some of this material can become unbound, drifting away from the collapsing star in a slow, low-energy outflow. In some theoretical models, as this weakly unbound material expands and cools, it can produce a faint optical transient. The material recombines, hydrogen atoms that had been ionized capture electrons, and this recombination releases a small amount of light. The result is a dim, red, slowly evolving brightening that lasts for days to weeks. But this transient is faint, extremely faint compared to a real supernova. A typical core collapse supernova reaches a peak luminosity roughly 1 billion times the luminosity of the Sun or more. The faint transient from a failed supernova might peak at only about 1 million times the luminosity of the Sun. That's a factor of roughly 1,000 times fainter than a normal supernova. It's visible, but only if you're looking carefully at the right galaxy at the right time, with a telescope sensitive enough to pick it up. In other models, the transient is even dimmer, or it doesn't happen at all. If the star's envelope is tightly bound, or if the star has lost its hydrogen envelope through stellar winds or binary interactions, there might be no optical transient whatsoever. The star simply fades. Its luminosity drops as the photosphere falls inward. The surface area shrinks, and eventually everything is behind the event horizon. The star goes dark. This presents an extraordinary observational challenge. How do you detect something that is defined by its absence? How do you find a star that disappears without a trace? The answer is that you have to watch. You have to monitor large numbers of stars over and over, year after year, and look for one that vanishes. This is exactly what a team of astronomers led by Chris Kochenek at Ohio State University set out to do in the early 2000s. The strategy is conceptually simple, but logistically demanding. You take images of nearby galaxies close enough that you can resolve individual bright stars in them. You catalogue the massive luminous stars in those galaxies. Then you keep taking images month after month, year after year, and you compare. You look for massive stars that were present in earlier images and are absent in later ones. If a massive star disappears without a corresponding supernova being detected, it becomes a candidate for a failed supernova. The star died, but it didn't explode. It just went away. Kochenek's team used the Large Binocular Telescope in Arizona to monitor 27 galaxies regularly over many years. They weren't looking for bright explosions. They were looking for the opposite. They were looking for stars that stopped being there. They were hunting for ghosts, for absences, for the silence left behind when a massive star swallows itself. The practical reality of running such a survey is far more difficult than the concept suggests. You're not simply comparing two photographs and looking for a missing dot. You're working with images taken at different times, under different atmospheric conditions, with different exposure times, sometimes with different instruments. The brightness of every star in the image fluctuates from one observation to the next, simply because of changes in atmospheric seeing, instrument calibration, and pointing accuracy. You have to correct for all of these effects before you can meaningfully compare images. Then there is the problem of crowding. In a galaxy tens of millions of light years away, individual stars are faint and often close together on the sky. A single pixel in a telescope image might contain the blended light of several stars. When one star disappears, the pixel doesn't go dark, it just gets slightly fainter. You have to perform careful photometry, measuring the precise brightness of individual sources to detect the change. And you have to do this for thousands of stars in each galaxy, across multiple epochs, over years. False positives are a constant concern. Stars dim for many reasons that have nothing to do with failed supernovae. Massive stars undergo eruptions that can change their brightness dramatically. Dust can form in the winds of evolved stars, temporarily obscuring them. Stars in binary systems can be eclipsed by their companions. Long-period variable stars can fade to near invisibility at certain phases of their pulsation cycles, and then brighten again months later. For every genuinely disappeared star, there might be dozens of false alarms caused by these ordinary processes. Each one has to be investigated and ruled out, which takes time, telescope resources, and careful analysis. There is also the simple problem of patience. You have to maintain a survey for years, sometimes decades, to build up a reliable baseline of observations. A star that disappears between two observations taken 6 months apart might reappear if you wait another year. You can't declare a star missing after a single non-detection. You need multiple follow-up observations at multiple wavelengths, spread over several years, to be confident that the star is truly gone and not merely hiding temporarily. And in 2015, they reported the most compelling candidate for a failed supernova ever found. The star was designated N6946-BH1, located in the galaxy NGC 6946, often called the Fireworks Galaxy. NGC 6946 earned that nickname because it has produced an unusually high number of observed supernovae. At least 10 supernovae have been recorded in this galaxy over the past century, more than almost any other known galaxy. It's a prolific producer of stellar death, but in this case, the galaxy appears to have produced something different. Not a supernova, a disappearance. N6946-BH1 was a red supergiant star with an estimated mass of about 25 solar masses and a luminosity roughly 300,000 times that of the Sun. It was clearly visible in images taken by the Hubble Space Telescope and the Spitzer Space Telescope in the mid-2000s. It was a real, identifiable, catalogued star. Bright, massive, exactly the kind of star that should eventually produce a supernova. In 2009, something happened. The star brightened slightly. Its luminosity increased modestly over a period of several months. This is consistent with what some theoretical models predict for the early stages of a failed supernova. The weak shock or the disturbance propagating through the hydrogen envelope can cause a brief increase in brightness before the star fades. The brightening was not dramatic. It wasn't anywhere close to what a real supernova looks like. It was a subtle increase, visible in the data but not the kind of thing that would attract attention in a routine survey. Then the star began to fade. Its optical luminosity dropped. Over the following months and years, the star became dimmer and dimmer in visible light. By around 2015, the star had essentially disappeared in optical wavelengths. Hubble images of the same region showed nothing where the star had been. The red supergiant was gone. But here's an important detail. The star did not simply vanish from every wavelength simultaneously. Its disappearance unfolded over years, and the sequence of changes across different wavelengths told a story that astronomers had to read carefully and patiently. The timeline of observations is worth walking through carefully because it shows just how methodical this process had to be. The initial identification of the star relied on archival Hubble images taken in 2004 and 2007 using optical filters. In those images, the star was clearly visible, a bright red source consistent with a red supergiant of roughly 25 solar masses. Spitzer Space Telescope observations in the mid-infrared confirmed the star's presence and gave additional information about its temperature and luminosity. The star was real, well characterized, and sitting exactly where the theory predicted a failed supernova candidate might be found. A massive red supergiant in a galaxy close enough to resolve individual stars. When the modest brightening occurred around 2009, it was not immediately recognized as significant. Red supergiants are variable stars. They pulsate. They change brightness on timescales of months to years. A star getting slightly brighter or dimmer is not unusual. This is one of the fundamental challenges of this kind of work. You're looking for a subtle signal buried in natural noise. Every massive star in your survey fluctuates. Every one of them brightens and dims to some degree. You have to distinguish the normal breathing of a living star from the final gasp of a dying one. And in the moment, those two things can look very similar. It was only as the star continued to fade in subsequent years, dropping in optical luminosity steadily and persistently rather than recovering as a variable star would, that the team began to take the event seriously as a potential failed supernova. By 2012 and 2013, the optical fading was unmistakable. The star was significantly dimmer than it had been in the archival images, and by 2015, it was effectively gone in optical light. The infrared data told a complementary story. In the years immediately following the optical fading, the Spitzer telescope detected a source at the star's position that was actually brighter in the infrared than the original star had been. This is a critical detail. When a star is merely hidden behind a dust shell, you expect exactly this behavior. The dust absorbs the star's optical light and re-emits it in the infrared. The total energy output stays roughly the same. It just shifts to longer wavelengths. So initially the infrared brightening was consistent with either a failed supernova or a dust-obscured star. But then the infrared source began to fade as well. By 2016 and beyond, the infrared luminosity was declining. This is not what you would expect if the star were alive and merely hidden behind dust. A living star would continue to heat the dust, maintaining the infrared emission. The fact that the infrared was fading indicated that the energy source itself was disappearing. Whatever had been powering the emission was going away. This is consistent with a small amount of material ejected during the collapse, now expanding, cooling, and fading as no new energy source remains to sustain it. The furnace had been extinguished. The residual glow was dying out. The team also had to rule out the possibility that the star had simply moved behind a dense molecular cloud in its host galaxy. This was unlikely given the timescale and the specific location, but it had to be checked. They examined the surrounding region for evidence of new obscuring material and found none. They compared images at multiple wavelengths to look for any sign that the star was still present but hidden. They found no evidence of a surviving source. No supernova was detected. Astronomers around the world monitor NGC 6946 closely because of its history of producing supernovae. If a normal supernova had occurred, it would have been noticed. Multiple supernova surveys were operating during this period. The galaxy was being watched, but no explosion was reported. The star brightened slightly, then disappeared. That's it. That's the whole story from an observational standpoint. This is exactly what theoretical models predict for a failed supernova involving a red supergiant. A brief, modest brightening as the outer envelope responds to the core collapse. A gradual fading in optical light as the photosphere recedes and material falls inward. A period of infrared emission from warm dust or weakly ejected material, and then silence. No explosion, no remnant nebula, no pulsar. Just a black hole sitting in the darkness where a massive star used to be. The Kochanek team has been careful to present N6946-BH1 as a strong candidate rather than a confirmed failed supernova. And this caution is appropriate because there are other possible explanations for a disappearing star. The star could have experienced a massive eruption, a giant outburst that ejected a thick shell of dust, obscuring the star from view. Some very massive stars, particularly luminous blue variables, undergo enormous eruptions that can temporarily hide them behind dust clouds. If this happened, the star might still be there, hidden behind the dust, waiting to become visible again as the dust disperses. However, the long timeline of the disappearance and the fading of the infrared source work against this interpretation. If the star were merely hidden behind a dust shell, we would expect the infrared emission to remain strong or even increase as the dust absorbs the star's light and re-emits it at longer wavelengths. Instead, the infrared emission has faded, consistent with the star genuinely going away rather than being hidden. Another possibility is that the star did produce a supernova, but an extremely faint one that was missed by surveys. This is unlikely given how closely NGC 6946 is monitored, but it can't be entirely ruled out. Some supernovae are genuinely faint, and if the explosion happened during a period when the galaxy wasn't being observed, it could have been missed. But this is considered unlikely by most researchers, given the timing and the available data. There's also the question of whether the star might have experienced a different kind of stellar death entirely. Maybe a merger with a binary companion, maybe an unusual type of eruption that consumed most of the star's luminosity. The universe is creative, and stars can die in ways we don't fully anticipate. But the properties of N6946-BH1, its mass, its luminosity, its spectral type, and the way it disappeared, all match the theoretical predictions for a failed supernova remarkably well. It remains the single best candidate we have. There is another intriguing case worth discussing. In 2019, astronomers reported that a massive luminous blue variable star in the dwarf galaxy PHL 293b appeared to have vanished. This star was enormously luminous, estimated at roughly 2.5 million times the luminosity of the Sun, corresponding to a star of perhaps 75 to 100 solar masses. The star had been observed spectroscopically in earlier years, and its signature was clearly present. But in observations taken around 2019, the spectral signatures of the star were gone. It had either disappeared or changed dramatically. This case is different from N6946-BH1 in several important ways. The galaxy is much farther away, roughly 75 million light years, compared to about 22 million light years for the Fireworks galaxy. The star was not a red supergiant, but a luminous blue variable, a very different type of massive star, and the interpretation is less clear. The star might have collapsed into a black hole without a supernova, but it's also possible that the star underwent a massive eruption, becoming obscured by ejected material. Luminous blue variables are known for dramatic instability and giant eruptions that can temporarily change their appearance completely. The case remains ambiguous and more observations are needed. Beyond searching for disappearing stars in optical and infrared light, there's another way to detect failed supernovae, and it might ultimately prove to be the most definitive. Neutrinos. As we discussed earlier, both successful and failed supernovae produce enormous bursts of neutrinos during the core collapse. The difference is in how the neutrino signal ends. In a successful supernova, the proto-neutron star survives and slowly cools, emitting neutrinos at a declining rate over a period of roughly 10 to 20 seconds. The neutrino signal fades gradually. In a failed supernova, the proto-neutron star collapses into a black hole, and the neutrino signal is abruptly cut off. One moment, neutrinos are streaming out. The next moment, they stop. This sudden cut-off is a distinctive signature. Current neutrino detectors like Super Okande in Japan and IceCube at the South Pole are sensitive enough to detect the neutrino burst from a core collapse within our own galaxy. If a massive star in the Milky Way were to undergo a failed supernova, these detectors would pick up the neutrino signal. They would see the initial burst as the core collapses and the proto-neutron star forms. And then they would see the signal suddenly stop, far sooner than expected, as the black hole forms and swallows the neutrino source. No corresponding optical supernova would be detected. The combination of a neutrino burst with an abrupt cutoff and no visible explosion would be extremely strong evidence for a failed supernova. Let me walk you through what this would actually look like if it happened. Imagine a massive red supergiant somewhere in the Milky Way, perhaps 10,000 light years away, begins its core collapse. Within seconds, the detectors at Super Okande and IceCube and other facilities around the world begin registering neutrino events. Thousands of neutrinos, far more than the 25 detected from SN 1987A, because this star would be much closer. The neutrino signal rises sharply, reflecting the initial collapse and the formation of the proto-neutron star. For the first few hundred milliseconds, the signal looks exactly like what we would expect from a normal supernova. The neutrino luminosity is intense and sustained as the proto-neutron star radiates its binding energy. But then, instead of gradually declining over 10 to 20 seconds as the proto-neutron star slowly cools, the signal simply stops. Within a few milliseconds, the neutrino count drops from thousands of events per second to 0. Not a gradual fade, a hard cutoff, an abrupt silencing. The proto-neutron star has collapsed into a black hole, and the neutrino-emitting surface has vanished behind the event horizon. This sudden termination would be immediately distinctive in the data. A successful supernova produces a neutrino light curve that declines smoothly over many seconds, like a bell curve with a long tail. A failed supernova produces a neutrino light curve that rises and then drops off a cliff. The difference between these two shapes would be obvious to any physicist analyzing the data. Within hours, the neutrino community would know that something unusual had happened. A core collapse had occurred, but it had terminated prematurely. Then the waiting would begin. Astronomers would point optical and infrared telescopes toward the position on the sky from which the neutrinos had arrived. They would search for a brightening supernova. They would wait days, then weeks, and nothing would appear. No supernova, no brightening star. Perhaps a faint infrared glow from loosely ejected material. Perhaps nothing at all. The neutrinos would have told us that a star died, and the telescopes would confirm that it died silently. The combination of these two pieces of evidence, a neutrino burst with an abrupt cutoff and no optical counterpart, would be as close to definitive proof of a failed supernova as we could hope for. The challenge is that core collapses within the Milky Way are rare. The estimated rate is perhaps 1 or 2 per century, and only a fraction of those would be failed supernovae. So we might have to wait decades or even longer for such an event. But when it happens, if it happens during a time when our neutrino detectors are operating, the signal would be unmistakable. Next generation neutrino detectors like Hyper-Kami Okande, currently under construction in Japan, will be even more sensitive. They'll be able to detect neutrinos from core collapses in nearby galaxies as well, not just the Milky Way. This dramatically increases the chances of catching a failed supernova in the act. If we could detect the neutrino burst from a core collapse in the Fireworks galaxy or another nearby galaxy, and if that neutrino burst showed the characteristic sudden cutoff, and if no corresponding supernova appeared in the optical data, the case for a failed supernova would be essentially closed. There's also the possibility of detecting failed supernovae through gravitational waves. When a core collapses, whether successfully or not, it produces gravitational waves. These are ripples in space-time caused by the asymmetric motion of massive amounts of matter. Current gravitational wave detectors like LIGO and Virgo are sensitive to mergers of compact objects, black holes, and neutron stars spiraling together and colliding. They're not currently sensitive enough to detect the gravitational wave signal from a core collapse unless it happens very close by, within the Milky Way or its immediate satellite galaxies. But future detectors might change this. If we could detect the gravitational wave signal from a core collapse and correlate it with neutrino observations and optical monitoring, we would have an extraordinarily complete picture of what happened inside the star. The observational search for failed supernovae is also being transformed by a new generation of survey telescopes. The Vera C. Rubin Observatory in Chile, which began its primary survey operations recently, is designed to image the entire visible sky every few nights. Its Legacy Survey of Space and Time, or LSST, will monitor billions of objects repeatedly over 10 years. This cadence is perfectly suited for detecting disappearing stars. If a massive star in a nearby galaxy vanishes between one observation and the next, the Rubin Observatory will notice. The sheer volume of data this telescope produces will allow astronomers to systematically search for failed supernovae across thousands of galaxies simultaneously. This is a fundamental shift in how we search for these events. The Kocherneck team monitored 27 galaxies over many years and found one strong candidate. The Rubin Observatory will monitor thousands of galaxies, potentially finding dozens of candidates over the coming decade. This will transform the study of failed supernovae from a field with one candidate and a lot of theory into a field with robust statistics and real observational constraints. But there's an inherent difficulty in this search that will never fully go away, and it's worth being honest about it. Proving that a star died as a failed supernova requires proving a negative. You have to demonstrate that the star didn't just become hidden behind dust. You have to demonstrate that there wasn't a faint supernova that was somehow missed. You have to demonstrate that the star didn't undergo some of the kind of dramatic change that mimicked a disappearance. Proving that something didn't happen is always harder than proving that something did happen. A supernova is easy to confirm. It's bright. It matches known light curve templates. It produces spectral signatures that are well understood. A failed supernova, by contrast, is defined by the absence of all those things. It's defined by what you don't see. This is why the combination of different observational channels is so important. Optical monitoring alone can tell you that a star disappeared, but it can't tell you definitively why it disappeared. Add infrared monitoring, and you can check whether the star is hidden behind dust. Add neutrino detection, and you can check whether a core collapse occurred and whether a black hole formed. Add gravitational wave detection, and you can independently confirm the collapse. Each additional channel of information makes the case stronger. No single observation can prove a failed supernova beyond all doubt. But the convergence of evidence from multiple channels can make the case overwhelming. There's one more observational consequence of failed supernovae that deserves attention. If a significant fraction of massive stars die without producing visible explosions, then the observed supernova rate should be lower than the rate at which massive stars die. In other words, if you count the number of massive stars being born in a galaxy and compare it to the number of supernovae observed in that galaxy, the numbers should not match. There should be a deficit of supernovae. Some massive stars should be dying without producing visible explosions, and this missing fraction should show up as a gap between the birth rate of massive stars and the death rate as measured by supernova counts. This comparison is difficult to make precisely because measuring stellar birth rates and supernova rates both involve significant uncertainties, but several studies have attempted it, and the results are suggestive. The observed supernova rate in nearby galaxies does appear to be somewhat lower than what you would expect based on the rate of massive star formation. The deficit is not enormous, but it is consistent with a failed supernova fraction of roughly 10 to 30%, which aligns with what theoretical models predict. This is not proof, but it is a piece of circumstantial evidence that supports the idea that some massive stars are dying without producing observable explosions. The picture that emerges from all of this is one where stellar death is more varied and more subtle than most people imagine. The popular image of a supernova, a massive star exploding in a blaze of light bright enough to outshine a galaxy, is real. It happens. It's been observed thousands of times across the universe, but it's not the only way a massive star can die. Some massive stars may reach the end of their lives, undergo core collapse, and simply vanish. They produce no blinding flash. They scatter no newly forged elements across space. They leave behind no glowing remnant. They just go dark, replaced by a black hole that reveals its presence only through its gravity. And the only way we can catch them is by watching, patiently and carefully, for stars that were there yesterday and aren't there today. In a sense, searching for failed supernovae is the opposite of most astronomy. Most of the time, astronomers look for things that appear. a new comet, a bright supernova, a gamma ray burst, a gravitational wave signal. These are events that announce themselves, that arrive in our data uninvited and demand attention. Failed supernovae don't announce themselves. They don't demand attention. They require attention. They require astronomers to know what was there before and to notice that it's gone. They require the patience to monitor the same galaxies year after year, checking on the same massive stars, waiting for one of them to silently slip away. And that's perhaps what makes failed supernovas so fascinating. Not the violence of the collapse, which is every bit as extreme as a normal supernova. Not the formation of the black hole, which is remarkable in its own right. But the silence. The universe's most massive stellar collapses, involving more energy than the human mind can meaningfully comprehend, can unfold in near-perfect silence. No light, no explosion, no fanfare. Just a star that was there, and then wasn't, and a darkness that remains. Everything we've discussed so far, the physics of the stalled shock, the formation of the black hole, the quiet disappearance of a massive star, might sound like an exotic edge case, a curiosity buried deep in the technical literature of astrophysics. Something that happens occasionally but doesn't really matter for the big picture. But that's not the case. Failed supernovae, if they occur at the rates that current models suggest, have profound consequences for how we understand stellar death, how we account for the black holes populating the universe, how we interpret the chemical enrichment of galaxies, and how we think about the fundamental question of which stars explode and which ones don't. This is not a footnote. It rewrites parts of the story we thought we already understood. Let's start with something called the red supergiant problem. For years, astronomers have been trying to match the supernovae they observe with the stars that produce them. The way you do this is straightforward in principle. When a supernova goes off in a nearby galaxy, you go back and look at images of that galaxy taken before the explosion. If you're lucky, the progenitor star, the star that exploded, is visible in those earlier images. You can measure its brightness, its color, and its temperature. From those measurements, you can estimate its mass. Over the past 2 decades, astronomers have identified the progenitor stars of dozens of core collapse supernovae, and a pattern has emerged that's difficult to explain. The progenitors of the most common type of core collapse supernova, called Type II plateau supernova, are consistently red supergiants. This makes sense. Red supergiants are massive stars in the final stages of their lives, exactly the kind of stars that should undergo core collapse. But here's the problem. The red supergiants identified as supernova progenitors tend to have masses between about 8 and roughly 16 to 18 solar masses. Above that range, the progenitors seem to disappear. Astronomers don't find red supergiant progenitors with masses of 20, 25, or 30 solar masses, even though such stars clearly exist. We can see them in galaxies. We know they're there. They should be dying and producing supernovae. But when a supernova goes off, the progenitor is almost never one of these high-mass red supergiants. This absence was first highlighted by the astronomer Stephen Smart and his collaborators, who systematically compiled data on supernova progenitors and pointed out the statistically significant deficit of high-mass red supergiant progenitors. The upper mass limit for observed progenitors seems to be around 16 to 18 solar masses. Above that, the cupboard is bare. This became known as the red supergiant problem, and for years it puzzled astronomers. Where are the explosions of the most massive red supergiants? There are several possible explanations. One is that the most massive red supergiants lose their hydrogen envelopes before they die, transitioning into a different kind of star, a Wolf-Rayet star, or a stripped helium star, and producing a different type of supernova that looks different from a Type II plateau. In this scenario, the stars do explode, but they don't look like red supergiant explosions because they've shed their outer layers. This is a real possibility and almost certainly explains some of the missing progenitors, but it's unlikely to explain all of them. Mass loss rates would have to be very high to strip the envelopes of all red supergiants above 18 solar masses, and observations of red supergiants in nearby galaxies show that many of them retain their hydrogen envelopes right up until the end. The other explanation, and the one that connects directly to everything we've been discussing, is that the most massive red supergiants don't explode at all. They undergo failed supernovae. They collapse directly into black holes. Their cores give out, their shocks fail, and they disappear. If this is what's happening, then the red supergiant problem is not really a problem at all. It's exactly what you'd expect. The most massive red supergiants are absent from the supernova progenitor sample, not because they exploded as a different type of supernova, but because they didn't explode. They died silently. They vanished. And because they didn't produce a visible supernova, there is no explosion to trace back to a progenitor. The star simply isn't there anymore. This interpretation is consistent with the theoretical models we discussed earlier. The most massive red supergiants, those above roughly 20 solar masses, tend to have higher compactness parameters and more tightly bound envelopes. They're exactly the stars where the neutrino-driven shock revival mechanism is most likely to fail. If failed supernovae are responsible for the red supergiant problem, then the mass dividing line between stars that explode and stars that fail should be somewhere around 16 to 20 solar masses, give or take, and that's remarkably close to what the theoretical models predict. N 6946-BH1, the disappearing star in the Fireworks galaxy, had an estimated mass of about 25 solar masses. It was a red supergiant. It was above the apparent mass limit for observed supernova progenitors, and it vanished without a supernova. If this is indeed a failed supernova, it fits the picture perfectly. It's exactly the kind of star that should fail to explode according to the theory, and it's exactly the kind of star that's missing from the supernova progenitor sample. Now let's talk about black holes, because failed supernovae change how we think about the population of black holes in the universe. Before the detection of gravitational waves, the stellar mass black holes we knew about were found in X-ray binary systems, where a black hole orbits a normal star and strips material from it. The accreting material heats up and emits X-rays, revealing the black hole's presence. The black holes in these systems typically have masses of about 5 to 15 solar masses. For a long time, astronomers assumed that these black holes formed in normal, core collapse supernovae. A massive star explodes, ejects most of its mass, and the remaining core collapses into a black hole. In this scenario, the black hole mass is limited by how much material falls back after the explosion. Most of the star's mass is ejected, so the black hole ends up being much less massive than the original star. But then gravitational wave detectors changed everything. On September 14th, 2015, the LIGO detectors made their first detection of gravitational waves. The signal, designated GW150914, came from the merger of two black holes with masses of about 36 and 29 solar masses. The merged black hole had a mass of about 62 solar masses. These masses were shocking. 36 and 29 solar masses were far larger than any stellar mass black holes previously observed in X-ray binaries. How could black holes this massive form? One possible answer is failed supernovae. If a massive star collapses directly into a black hole without a supernova explosion, it retains most or all of its mass. A star with an initial mass of 40 solar masses that loses perhaps 5 to 10 solar masses through stellar winds over its lifetime could produce a black hole of 30 to 35 solar masses through direct collapse. No explosion, no mass ejection. The star simply becomes the black hole. This is especially relevant for stars with low metallicity. Remember, metallicity affects how much mass a star loses through winds. Low metallicity stars retain more of their original mass. In the early universe, when metallicity was lower, massive stars would have been more likely to retain their full mass and more likely to produce failed supernovae. This means the early universe could have been a prolific factory for massive black holes. Black holes in the 20 to 50 solar mass range or even higher formed through the direct collapse of massive stars that never exploded. Since that first detection, LIGO and Virgo and KHGRA have detected dozens of black hole mergers. The masses of these black holes span a wide range, from a few solar masses to nearly 100. The distribution of masses contains information about how black holes form, and the existence of a population of black holes in the 20 to 40 solar mass range is consistent with a significant contribution from failed supernovae. These are black holes too massive to easily explain through normal supernovae, where most of the star's mass is ejected, but perfectly natural if the stars collapsed whole. There's a related puzzle that makes the connection between failed supernovae and gravitational wave observations even more interesting. It's called the mass gap. When astronomers look at the known population of compact objects, neutron stars and black holes, they notice something strange. Neutron stars tend to have masses between about 1 and 2 solar masses. The heaviest confirmed neutron stars are around 2 to 2.5 solar masses. Stellar mass black holes in X-ray binary systems tend to start at about 5 solar masses and go up from there. But between roughly 2.5 and 5 solar masses, there seems to be a gap. Very few compact objects have been found in this mass range. If massive stars always explode as successful supernovae, you might expect a smooth continuum of remnant masses. Some stars would leave behind heavy neutron stars. Others would leave behind light black holes. The mass distribution should be continuous, but the gap suggests that the process of forming compact remnants is not smooth. Something about the physics creates a jump, skipping over that intermediate mass range. Failed supernovae offer a potential explanation. In a successful supernova, the explosion ejects most of the star's mass. The compact remnant forms from whatever material falls back onto the proto-neutron star after the explosion. This fallback is limited by the energy of the explosion. A strong explosion ejects more material, leaving a lighter remnant. A weaker explosion allows more fallback, producing a heavier remnant. But there's a ceiling. If the explosion is strong enough to succeed at all, it's generally strong enough to eject enough material that the remnant stays below a certain mass. In a failed supernova, by contrast, there is no explosion. There is no ejection. The proto-neutron star simply grows until it collapses into a black hole, and then the rest of the star follows. The resulting black hole inherits most of the star's final mass. It doesn't form gradually through fallback. It forms suddenly and completely. This means the black hole starts heavy, jumping directly from the proto-neutron star stage to a black hole of many solar masses. This sudden transition could be exactly what creates the mass gap. Stars that explode successfully produce remnants below the gap. Neutron stars up to about 2.5 solar masses. Stars that fail to explode produce remnants above the gap, black holes of 5 solar masses or more. The gap itself exists because there is no intermediate process. You either explode and leave a light remnant, or you don't explode and leave a heavy one. There's nothing in between because the physics doesn't allow a half-successful supernova in the way that would be needed to populate the gap. Some gravitational wave detections have hinted at objects within the mass gap, which would complicate this picture, but the overall framework, where the mass gap is a natural consequence of the bimodal nature of stellar death, either full explosion or full collapse, is compelling and is being actively tested against new data. There's another implication that reaches even deeper into astrophysics. Supernovae are the primary mechanism by which heavy elements are distributed through galaxies. When a star explodes, it scatters carbon, oxygen, silicon, iron, and elements heavier than iron into the surrounding interstellar medium. These elements become part of gas clouds that eventually form new stars and planets. Without supernovae, the universe would be made almost entirely of hydrogen and helium. There would be no rocky planets, no liquid water, no organic chemistry, no life as we know it. If a significant fraction of massive stars fail to explode, those stars take their heavy elements with them into the black hole. The carbon, oxygen, silicon, and iron that were forged over millions of years of nuclear burning are not returned to the galaxy. They're locked away behind the event horizon, permanently removed from the cosmic cycle of element recycling. Let me make this concrete. Consider a star born with 40 solar masses. Over the course of about 5 million years, this star fuses hydrogen into helium in its core. Then helium is converted into carbon and oxygen. Then carbon into neon and magnesium. Then neon converts into oxygen and more magnesium. Then oxygen into silicon and sulfur. Then silicon into iron. At each stage, the star builds up layers of different elements, like the layers of an onion. By the time the iron core forms, this star contains enormous quantities of heavy elements. Tons is too small a word. This star has produced solar masses worth of carbon, solar masses of oxygen, solar masses of silicon, and a core of iron weighing more than the sun itself. In a successful supernova, all of this material, or most of it, gets blasted into space. The carbon drifts through the interstellar medium and eventually becomes part of a new gas cloud. That cloud collapses to form a new star and planets. The carbon ends up in the atmospheres of those planets, in their oceans, in organic molecules, in living cells. Every one of those elements was destined to be scattered into the galaxy. In a successful supernova, they would have drifted through the interstellar medium for millions of years, eventually seeding new gas clouds, new stars, new planets, new possibilities for chemistry and complexity. That is the normal cycle. That is how the universe builds on what came before. Each generation of stars inherits the elements forged by the generation that preceded it, and adds its own contributions before passing them along. Now consider what happens if that same 40 solar mass star undergoes a failed supernova instead. The iron core collapses, the shock stalls, the black hole forms, And then every layer of that stellar onion, the iron, the silicon, the oxygen, the carbon, the helium, the hydrogen, all of it falls past the event horizon. 5 million years of nuclear burning, 5 million years of element creation, all of it locked away permanently. None of it will ever become part of a new star. None of it will ever form a planet. None of it will ever be incorporated into a living organism. It is gone, not destroyed, because the black hole still has mass, but removed from the universe's accessible inventory of matter forever. The universe spent 5 million years cooking those elements inside that star, and then gravity ate the entire meal and left nothing on the table. Multiply this by the millions of massive stars that may have undergone failed supernovae over the history of the universe, and you begin to see how the chemical evolution of galaxies could be significantly affected. Entire stellar lifetimes of nucleosynthesis erased. Elements that should have been recycled into new generations of stars and planets swallowed whole. The universe is poorer for it. Not by a catastrophic amount, but measurably, meaningfully poorer. This means that failed supernovae reduce the rate at which galaxies are enriched with heavy elements. The effect might be modest if only 10 to 15% of massive stars fail, but if the fraction is closer to 20 or 30%, it could have measurable consequences for the chemical evolution of galaxies, particularly in the early universe when metallicity was already low and failed. Supernovae may have been more common. This also affects how we model the evolution of galaxies over cosmic time. Galaxy evolution models track the birth and death of stars, the production and distribution of heavy elements, the formation of new generations of stars from enriched gas. These models need to know what fraction of massive stars return their heavy elements to the galaxy through supernovae, and what fraction lock those elements away in black holes. Getting this wrong means getting the chemical evolution of galaxies wrong, which means getting the formation histories of stars and planets wrong. Failed supernovae are not just an interesting curiosity, they're a missing variable in the equations that describe how galaxies work. There's also a subtler but equally important implication related to the energy that supernovae inject into the interstellar medium. Supernova explosions don't just scatter elements, they also deposit enormous amounts of kinetic energy into the surrounding gas. This energy drives turbulence, compresses gas clouds, triggers new episodes of star formation, and can even blow gas out of galaxies entirely. Supernova feedback, as it's called, is one of the primary mechanisms regulating star formation in galaxies. Without it, galaxies would form stars much more efficiently, consuming their gas supply quickly and producing far more stars than we actually observe. If some supernovae fail, the energy they would have injected into the interstellar medium is lost. The gas surrounding the dead star doesn't get disturbed. No shockwave compresses nearby clouds. No new star formation is triggered. The neighborhood remains quiet. Over time, this deficit in energy injection could affect the overall star formation rate of a galaxy and the structure of the interstellar medium. This is another factor that galaxy evolution models need to account for, and it's one that has only recently begun to be incorporated. Now, I want to be honest about what we don't know, because there is a great deal of uncertainty remaining. The physics of core collapse supernovae is extraordinarily complex. Even with the most powerful supercomputers in the world, fully three-dimensional simulations of core collapse with all the relevant physics included, neutrino transport, nuclear physics, general relativity, magnetic fields, rotation, turbulence. These simulations are at the absolute frontier of computational capability. They take months to run. They require approximations and simplifications that might affect the results. Different research groups using different codes and different approximations sometimes get different answers. The boundary between explosion and failure is not sharply defined. In some simulations, a star with a given mass explodes. In others, using slightly different physics or slightly different numerical methods, the same star fails. This sensitivity means that our predictions about which specific stars will fail and which will succeed are not yet precise enough to make definitive statements. We can identify trends. We can say that higher compactness generally leads to higher failure rates. We can say that the most massive red supergiants are the most likely candidates for failure. But we cannot point to a specific star in the sky tonight and say with certainty whether it will produce a successful supernova or a failed one when it eventually dies. The role of rotation and magnetic fields adds another layer of uncertainty. Most of the theoretical work on failed supernovae has focused on non-rotating or slowly rotating stars. But real stars rotate, and some massive stars rotate quite rapidly. Rotation can affect the core collapse process in complex ways. It can provide additional support against collapse. It can modify the geometry of the neutrino heated region. It can drive jets, bipolar outflows of material along the star's rotation axis, which might provide an alternative mechanism for exploding the star even when the standard neutrino mechanism fails. Magnetic fields are another wildcard. Some massive stars have strong magnetic fields that can become enormously amplified during core collapse. These fields could drive magnetohydrodynamic jets that carry energy away from the proto-neutron star and deposit it into the outer layers of the star. In some models, magnetically driven explosions can succeed even when the neutrino mechanism alone would have failed. This is particularly relevant for the most massive and rapidly rotating stars, where the neutrino mechanism is weakest, but the potential for magnetic effects is greatest. If magnetic jets can rescue some stars from failed supernovae, then the actual rate of failure might be lower than what neutrino-driven models alone predict. This is an active area of research, and the answer is not yet clear. Some groups find that magnetic effects can produce explosions in stars that would otherwise fail. Others find that the magnetic fields need to be unrealistically strong to make a difference. The truth probably depends on the specific properties of each star, its rotation rate, its magnetic field strength, and its internal structure. Binary interactions add yet another complication. Most massive stars are not alone. They exist in binary systems, orbiting another star. The companion star's gravity can strip material from the primary star's envelope during its life, dramatically altering its structure by the time it reaches core collapse. A star that would have had a massive, tightly bound hydrogen envelope as a single star might have lost most of the envelope to its companion, arriving at core collapse as a much more compact, stripped star. This could change the outcome from failure to success, or vice versa, depending on how the stripping affects the star's compactness and binding energy. The candidate events we have are also few in number. N6946-BH1 remains the strongest candidate, but it is essentially one event. One event does not make a robust statistical sample. You cannot determine a rate from a single detection. You cannot draw firm conclusions about the mass boundary between explosion and failure from one star. You need more candidates, many more to start building a real observational picture. This is why the coming decade is so important. The Vera C. Rubin Observatory, with its LSST survey, will monitor hundreds of millions of stars in thousands of galaxies over 10 years. It will have the sensitivity and cadence to detect disappearing stars systematically. If failed supernovae occur at rates of 10 to 30% of all core collapses, the Rubin Observatory should find multiple candidates, perhaps dozens, over the course of its survey. Each candidate will need follow-up observations with other telescopes to confirm the disappearance, rule out alternative explanations, and characterize the event. But for the first time, we'll have enough candidates to do real statistics. We'll be able to measure the rate. We'll be able to determine whether there's a mass threshold above which stars consistently fail. We'll be able to test the theoretical predictions against real data. Neutrino astronomy is also advancing. Hyperkami Okande, the next generation neutrino detector in Japan, will be significantly more sensitive than its predecessor. Combined with IceCube and other detectors worldwide, the global network will be capable of detecting neutrino bursts from core collapses in the Milky Way, and possibly in nearby satellite galaxies. If a failed supernova occurs within this detection volume, the abrupt cutoff of the neutrino signal would provide the most unambiguous evidence possible. Gravitational wave astronomy is maturing as well. Next generation detectors will be sensitive enough to detect gravitational waves from core collapse events. If a nearby star collapses and forms a black hole, the gravitational wave signal combined with neutrinos and optical data would give us a complete multi-messenger portrait of a failed supernova. The James Webb Space Telescope is also playing a role. Its infrared sensitivity allows it to study the environments of candidate failed supernovae in unprecedented detail. It can look at the position of a disappeared star and search for faint infrared remnants, warm dust, or residual emission that might reveal what happened. It can study the progenitor populations of massive stars in nearby galaxies, helping us build a complete census of which stars explode and which don't. All of these observations will converge over the next decade or two to give us a much clearer picture of failed supernovae. We'll know whether they're common or rare. We'll know which stars fail and which succeed. We'll understand the physical conditions that determine the boundary between explosion and silence. And we'll be able to incorporate this knowledge into our models of galaxy evolution, element production, and black hole formation. But let me step back from the technical details for a moment and reflect on what all of this means at a deeper level. Because there's something genuinely profound about the existence of failed supernovae. Something that changes how you think about stellar death and about the universe itself. For as long as humans have studied the sky, we've associated stellar death with spectacle. A supernova is one of the most dramatic events in nature. Ancient astronomers recorded guest stars that appeared suddenly in the sky, shining brightly for weeks before fading. Tycho Brahe in 1572 and Johannes Kepler in 1604 each witnessed supernovae bright enough to see in daylight, events so startling they challenged the ancient belief that the heavens were fixed and unchanging. These explosions were celebrated, studied, and remembered precisely because they were impossible to ignore. When we think about how stars die, we think about explosions, we think about light, we think about drama. But the universe doesn't owe us drama. It doesn't arrange its physics for maximum visual impact. The same laws of gravity and nuclear physics that produce the most luminous explosions in the cosmos can also produce the most silent collapses. The same iron core that triggers a supernova in one star triggers a quiet disappearance in another. The physics doesn't change. The outcome does. There's something humbling about this. The universe's most massive stellar collapses, involving cores that are heavier, denser, and more energetic than the cores of stars that produce successful supernovae, can unfold without producing a single photon of visible light that would catch our attention. The biggest deaths can be the quietest. The most extreme events can be the most invisible. The star collapses, a black hole forms, and the universe simply moves on, with one fewer star shining in the darkness and one more region of space-time curved into a gravitational trap that reveals nothing about what went into making it. Think about what that means for the stars you see when you look up at night. Some of them are massive enough to eventually undergo core collapse. Betelgeuse, the red supergiant in Orion, will die in the next 100,000 years or so, or it might produce a spectacular supernova, brightening enough to be visible in daylight for weeks. Or it might not. It might collapse quietly, its light fading over months, replaced by nothing but empty sky where a bright red star used to be. We don't know which outcome Betelgeuse will choose, or more precisely, which outcome the physics of its internal structure will dictate, and we won't know until it happens. This uncertainty extends across the galaxy. Of the hundreds of billions of stars in the Milky Way, millions are massive enough to eventually undergo core collapse. Some fraction of those, perhaps 10 to 30%, may die without a visible explosion. They will vanish from the sky one by one over millions of years. Their disappearances noticed only by future astronomers, patient enough to watch for them. The black holes they leave behind will drift through the galaxy in silence, invisible unless they pass close to another star or interact gravitationally with something we can observe. The universe is filled with these silent remnants, black holes born from failed supernovae, scattered through every galaxy, each one the gravestone of a star that died without ceremony. We can't see them directly. We can barely detect them indirectly, but they're there. The evidence from gravitational wave detections tells us that stellar mass black holes are common. Many of them, perhaps most of the more massive ones, may have formed this way. Not through the spectacular death of a supernova, but through the quiet failure of one. Through a star that tried to explode and couldn't. Through a shockwave that stalled and never recovered. Through the formation of an event horizon that swallowed everything, including the evidence of how it formed. There is a strange beauty in this. We are used to the idea that the universe announces its most dramatic events with proportional fanfare. But failed supernovae teach us that this isn't always true. Sometimes, the most extreme gravitational collapses in the stellar universe produce not the brightest lights, but the deepest silences. Sometimes the end of a star's life is not a scream, but a whisper. And sometimes the whisper is so faint that the only way to hear it is to notice that a voice you used to hear has gone quiet. The next time you look up at the night sky and see the familiar constellations, the bright stars marking the shoulders and knees of Orion, the curve of Scorpius, and the cross of Cygnus, remember that some of those stars will one day die. Some of them will explode magnificently, scattering their elements across space, seeding new generations of stars and planets, but others may simply disappear, They'll be there 1 century and gone the next. No explosion. No remnant glowing in the dark. Just an empty patch of sky where something bright and massive used to be. And in that empty patch, invisible and silent, a black hole will sit. The only memorial to a star that burned for millions of years, and then, in its final moment, swallowed its own death. That's what a failed supernova really is. It's not a malfunction. It's not an error in the universe's programming. It's physics. It's what happens when gravity, which has been patiently pulling inward for the star's entire life, finally wins completely. Not just at the core, as it does in every core collapse, but everywhere. The whole star, the whole explosion, everything. Gravity takes it all, and what's left is darkness and silence and a curvature in space-time that will persist for eons, long after the light of the star that made it has been forgotten. Some of the biggest stars in the universe die without making a sound, and somehow, that might be the most astonishing thing about them. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the most extraordinary phenomena in the cosmos. And remember, the next time you look up at the stars, you're not just seeing light, you're seeing a question. Which of those stars will go out with a bang and which will simply go out? The universe knows the answer. We're still learning how to ask. Good night.